Welcome. This is meant to help you as you work through help you with the calculations as you work through the Hess's Law Calorimetry lab. So it's just there to help walk. So let's look at first let's look at the values of what we need. The first values we need to look at is just looking at the file. We're going to do 4 parts. Part 1 is testing the heat capacity of the calorimeter with hot and cold water. So we need the temperature, the volumes of the hot and cold, temperature of the hot and cold, and initial and temperature at final. Then they talk about heat capacity. Well, it talks about the mass, the specific heat, the density, the heat gain, heat loss, and heat capacity. And it shows you something of the calculations. I don't know why they use C sub P there and S there, but it's stupid. Okay, then we break into strong acid, strong base, mix them together, find the temperature of solution, color, heat, specific heat, moles, and all that jazz. And then find the delta H reaction. Then part C, we repeat it again for a weak acid, and D, we put them together. So, looking at this, I'll pull up Excel spreadsheet here. So, there's some things we should know right off the bat. And that is the heat capacity of water. That is a constant. That will not change. That is 4.184 joules per mole Kelvin. That is a constant for water. The density of water, we are not being super accurate, so the density is 1 gram per mil. Now, why are those important? Well, if I report the volume of the hot water and the density of the hot water is 1 gram per mil, if the volume were to say be 50 mils and the volume of cold being 50 mils, it's going to be density times volume to give us our mass. So 50 grams and 50 grams. We're just going to hypothetically put them in there. Now, the initial hot, you can find that out. I don't remember what it was. Was it 54? I don't care. Initial cold, 25. Now, as we find the final temperature of the cool and the final temperature of the hot would be the same. Let's say they're 30. So that means the heat lost by the hot water would be equal to 4.184 times 50 times the change from the TF minus the TI. So you'd be losing, negative 50,000, negative 5,020 joules. The heat gained by the cool would be 50 times the heat capacity times the change. So 30 minus 25. So we have a positive value. Now the heat gained by the calorimeter would have to sum up with this one to add up to this. So in this hypothetical situation, Q calorimeter plus Q cool would equal the inverse of Q hot. So whatever this is, divide by -1, and we minus this value. So that means the rest of the energy must have been absorbed into that calorimeter. Now, if that was the case, to calculate the heat capacity of the calorimeter, since the calorimeter's mass should not have changed, we would be taking this value and dividing by the change in temperature of the cool water. Because the water absorbed 5 degrees in this hypothetical scenario, and the calorimeter absorbed 5 degrees. The calorimeter will be the same temperature as in the cool water. So with that in mind, you could calculate a hypothetical heat capacity of those coffee cup calorimeters. Now, this is a completely wrong value. Don't be trying to pull off this value. I just bullshitted some numbers. Now, we mixed, say, 50 mils of base and 50 mils of acid. We used 25 mils of acid, but we diluted to 50. So hypothetically, the total mass of solution, 50 plus 50, is 100 mils. The density of water did not change, so it's be 100 grams. Now, hypothetically, the initial temperature of both solutions should be about the same. So if, for example, the temperature of the base, which I measured, was like, say, 22, whatever, and the final temperature was, say, 28. We're going to just, you don't have to calculate the final temperature of HCl. We're going to just mix them together. Now the moles. Moles are equal to the molarity times the volume in liters. So hypothetically, we're going to consider the limiting reactant when we do the last reaction. So when we do how much heat did the water absorb? Well, 100, the mass, times the heat capacity, times the change in temperature. We went from 28 to 20, from 22 to 28. Now the heat capacity of our calorimeter. Well, we need the heat capacity of the calorimeter times our change in temperature again. So the calorimeter absorbs that much heat as well. Now for the heat of reaction, we're going to take the negative sum of these two numbers. So whatever heat that these two absorbed were produced by this reaction. The sum of those two together would make our heat of reaction. Then finally, to calculate our delta H, would take our heat of reaction and would divide by our moles of the limiting reagent, the smallest number. And so that would calculate, oh man, that's a big number, but that's because this should be in kilojoules. So divided by 1,000 would get this into kilojoules. So this is saying, oh, in this hypothetical bullcrap number, I produced 145 kilojoules of heat. So you would repeat that again for part C. Exact same reactions, exact same way. The only change is we did not dilute our acetic acid. So you'd have a slightly greater moles of acetic acid, and so you'd have a slightly greater number when we divide. And then finally, the last step is you would figure out there's going to be some combination of delta H in this reaction and delta H in this reaction, and you're going to add or subtract them together to get this reaction. You're trying to figure out what energy would be produced to go from HC to H3O2 to H plus and C2H3O2 1 minus. You're trying to figure out what energy would be associated with that? And based on the reactions you did in part what I did, that you hypothetically would have done in part B, in part C, you figure out which way would you add those or subtract those reactions together to get this hypothetical reaction. That is our Hess's law problem that we're going to be doing. So we're utilizing calorimetry and Hess's law to find out a reaction that we cannot find directly. So, mind, hopefully this has been helpful. Hopefully you can use these numbers in your calculations in a way that will make this lab a lot easier. So, good luck. Godspeed. So.